In this section, we're going to be discussing functions that are one-to-one and also the inverse of functions. First, let's discuss one-to-one functions. To determine whether a function is one-to-one, a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. In other words, if x and a different x are not equal to each other, then they will go to two different images in their range. For example, let's say over here, this is my domain, which we also could call our input, and then we'll call our range, which is also called our output. In our domain, we have x's, and these are three different x's. In the range, we have lots of y's. In order for a function to be one-to-one, every single x has to go to a different y image. An example of something that is not one-to-one, I will draw here. Something that is not one-to-one would be an example of an x that might go to this y. This x might go to the same y. This is a function, but this function is not one-to-one. It is a function because by definition of a function, every image of x goes to exactly one y. In other words, an x cannot go to two different y's. This x could not split off and go to two different images of two different y's. So this is a function. It would pass the vertical line test if drawn in a Cartesian coordinate system, but it is not one-to-one because every x has to have a different image of y as its output. What about this one over here? Well, this isn't even a function. This is not a function because this particular x is going to two different images or two different y's in the range. We don't discuss whether it's one-to-one or not because it's not even a function. We only discuss whether it's one-to-one if it's already a function. These two first graphs were functions, the first one being one-to-one, the second one was not, but the last one was not even a function. To look at graphs of one-to-one functions, let's first below decide whether it is a function. Well, yes, it is, because you can see it passes the vertical line test. A function is defined as for every x, you have only one y value. So this passes the vertical line test. One-to-one says that for every y value, you can only have one x. In other words, this function is not one-to-one. Because for two different x values, for example, this x and this x that are not equal to each other, but their functions evaluated at that particular location are actually equal to each other. So this x has this y value, but this x also has the same y value. So these two different x values are pointing to the same y, and similar to this Venn diagram up here, which has two different x values pointing to the same y value. So this would not be one-to-one because two different x values have the same y value, or the value of the function at those x values. A simpler way to determine whether a graph is one-to-one is to do what's called the horizontal line test, which is opposite of the vertical line test for functions. The horizontal line test says if every horizontal line intersects the graph of a function f in at most one point, then the f is 1 to 1. So if I were to draw a horizontal line anywhere through this graph, I should only hit the graph one time, meaning for this particular y, I only hit one x. For this particular y value, I only hit one x. So this is 1 to 1. However, this graph is not, because for this particular y value, I'm going to have two different x values, meaning when two x's are not equal to each other, I'm going to get the same y value. So this is not 1 to 1. However, both of these are indeed functions. In order to be a function, it only has to pass the vertical line test. You can see a vertical line will pass through this graph only one time. So this is a function, as is this is a function. Even though they're both functions, only one was 1 to 1, where the other is not. So now we're going to move on to talking about the inverses of a function. Inverses of a function are basically the opposites, or what undoes the function and brings it back to its original state. Inverses you can think of as multiply and divide. Those are inverses of each other, because when you multiply 2 times 3, you can undo that by dividing the numbers. Adding and subtracting are inverses of each other. Square roots and an exponent of 2 are inverses of each other. The one will always undo the other. So an inverse of a function is undoing the function. If you have an x and it's being mapped to a y, well, what will bring it back to its original state? That's what's defined as being an inverse. In drawing a picture of this to give you a better idea of what that would look like, you have a domain and you have the range. These are both of functions. Well, if I have an x that's in the domain and I apply the function f to x, it brings it to its image of y. Well, how do I get y back to its original state? I apply the inverse of the function to bring it back to its original. So the domain of the original function f sends x to the range of f. But now if we look at this separate image down here, where this would be the original domain of the inverse, and it sends y to x, which then would be the range of the inverse. So you're going to notice that the original domain of the function and the range of the inverse will be the same. Also, the range of the original function and the domain of the inverse will also be the same. In order to find the inverse of a function defined by a set of ordered pairs, we can do that by finding the inverse of the following one-to-one function. Let's state also the domain and the range of the function and its inverse. So let's look at this problem here. We have a set of 7 different points on a graph. If I wanted to look at the graph, we can look at a very basic graph. -3, -27, just giving a sketch. -2, -8, -1, -1, and so on. This is the graph of x cubed. Okay? You can see that this is a function, for it passes the vertical line test. You could also see this is 1 to 1 because it passes the horizontal line test. But the question was saying, find the inverse. To find the inverse of a function, we simply will take all of the points and reverse the images of each other. Because remember, the x's in the original become the original y's of the inverse. So the x's become y's. So we're going to take these two coordinates and we're going to swap the location of those. So the inverse is going to be located at -27, -3. -8, -2. -1, -1, and so on. And you're going to see if we were to graph that inverse over here in the picture, the graph would look something like this. -27, -3, -8, -2, would look something like that. Okay? You're going to notice that the domain of the original function, the domain of the original black function, is all real numbers. But in this case, we're just going to list the x's. So -3, -2, -1, 0, 1, 2, 3. The range of the function then is the y values. So starting at -27, -8, -1, 0, 1, 8, and 27. Now those are going to flop, and the range of the function becomes a domain of the inverse, because the y of the function becomes the x of the inverse. The range of the inverse comes from the domain of the function. So based on these results, you're going to find that the domain of the f becomes the range of the inverse, and the range of the function becomes the domain of the inverse. In other words, if you took the inverse of the original function, you get back at x. If you look at it from the inside out, this says you have an x in the domain. When you apply the function to it, it takes it over to y. But then when you take the inverse of that, it brings you back to x. So let's verify that these two functions are indeed inverses of each other. In order to verify that they're inverses, you have to verify two things. You have to first verify that when you plug the function into the inverse, you get an x back. So first we're going to verify that the inverse of the original function is indeed equal to x. Then we'll also have to prove that if you take the function of the inverse, it works the other way as well. So we're going to have to prove both ways. First, let's take the function and plug it into the inverse. So we're taking this function, and anywhere you see an x in the inverse, we're going to plug this 4x plus 9 into the inverse. So we're going to assume that g is the inverse. So let's take this function f and plug it into this g here. So since the function, the inverse, we're going to say it's equal to g of x. Now we're going to take 4x plus 9 and plug it in for x. Does this in fact equal x? Well, up in the numerator you can see we have 4x plus 9 minus 9, which is 4x over 4, which is equal to x. So yes, it does check that direction, but we also have to check it in the opposite direction. Now we have to take what we suppose to be the inverse Well, we're checking to see if G is the inverse, and we're plugging G into F. So now we're going to take this value here and plug that into X of my original function. So we're going to take, again, we're going to take the inverse, which is x minus 9 over 4, and plug it into the original. So we've got 4 times x minus 9 over 4 plus 9. So we simplify. We'll see that those cancel. So we have x minus 9 plus 9, which is equal to x. So yes, this indeed does check as well. Since both ways check, these are inverses of each other. Let me show you a brief little sketch of what this looks like. If I were to graph this linear function right here, it has a y-intercept of 9 and a slope of 4. Let me show you the graph of g of x, which is supposed to be its inverse. That graph is going to look like this. In a minute, I'll show you why you could tell by looking at this that these are inverses of each other. For now, I just sketched the graph. Now what if we looked at this one down here? Let's start by taking G and plugging it into F. So let's see first if taking the inverse of the original is indeed equal to x. Well, if we take the original function and plug it into its supposed inverse, we're taking 2x plus 6 and plugging it in for x. So this becomes 1/2 2x plus 6 minus 3. Well, if I distribute the 1/2, it becomes x plus 3 minus 3, which is x. So that checks. Now we do the opposite direction. Now we see if the original function of the inverse is equal to x. So now we take the inverse. In this case, we're going to suppose g is the inverse, and we're going to plug all of this into x of the original function. So we have 2 times 1/2 x minus 3 plus 6. So when I distribute the 2, I get 1x minus 6 plus 6, which is equal to x. So that also checks. Now I'm going to look at again at a brief sketch of both of these. This original 2x plus 6 looks like a line going through the y-intercept of 6 with a slope of 2. This graph has a y-intercept of -3 with a slope of 1/2. It would look like that. So again, I'll come back to this graph in a minute to show you how I can prove that those are inverses of each other looking at the graph instead of looking at the algebraic method. So to obtain the graph of an inverse and the graph of a function, the graph of f and its inverse are symmetric with respect to this line. Okay, this line I will draw in green. You can see it's the dotted line right here. So this line is y equals x. It's the inverse line. For every x, there is a y. So for example, 1, 1 is on the graph. 2, 2 is on the graph. 3, 3 is on the graph. So every x equals the same value of the y. The inverse, let's say this is my function, the inverse of this function will be an exact symmetrical reflection of this graph over this oblique line on this side. So if I wanted to draw that over here, I could draw that like so. basically any point on the function is going to have the opposite xy's on the inverse. So to show you what I did there, look at this point right here, which is at 1.50. Well, on its inverse, the point 0, 1.5 will be a point on that graph. Because remember, the domain becomes the range, and the range becomes the domain. So every x becomes the y, and every y becomes the x. So for every point on this function, you could just displace the x and the y. So to go back up here now, I can tell that these are inverses of each other, because when I draw that y equals x line down the middle, you can see these are reflections of each other. Let's try two more. So I've already got the line y equals x as the symmetry line, and let's draw another graph. Let's say I have a function that starts at 3, 2, continues straight down to 0, -1, and then cuts over to -2, -2. And I want to draw this symmetric line over the line of symmetry. So I'm going to swap these 2 points. So 2, 3 will be a point on my graph. So 2, 3 will be a point on the inverse. Point -1, 0 will be a point on the graph. -2, -2 will be a point on the graph. And you can see that these two graphs are symmetric of each other over the y equals x line. Let's try another one. What if my original graph started at -3, 0, continued on to 0, 1, and then cut through over to 3, 1. Well, if I wanted to draw that over the symmetrical line, I would have a point at 0, -3, and then that point would continue on to 1, 0, and then that point would continue over to 1, 3. And you can see that those are symmetric of each other. Anytime the graph of the function and its inverse intersect, they will always intersect on the graph of y equals x. So you see the intersection point here is right on the symmetry line, same as over here. On to the last page to summarize the inverses. If you wanted to actually find the inverse algebraically of an equation, the first thing you do is replace any name of the function with y. Then exchange any x's for y. They will swap places. Then, if possible, solve for y. Then go back and replace the y with the name, the function, which is the inverse, and then prove that both the inverse of the original function is x, but also the function of the inverse is x, like we did on the previous page. So we're going to run through a few examples of finding inverses now.